All right. So today's review for the practice or for the quiz 3 tomorrow is just going to mainly focus on the practice quiz itself and going over the concepts through the PowerPoints and equations and such to make sure that we all have a decent understanding of what's going to happen. So I have to share screen. This one, I believe. Everyone see that?
Yes.
All right, cool. All right. So I went at this, no calculator, 13 minutes and no reviewing, and I pulled a 64 out of 100. So with reviewing plus a calculator tomorrow, I believe all of us should do very well. So let's see, because it's as he said, the breakdown is, I believe, 10 true and false valued at 2 points each, and then 20 multiple choice valued at 4 points each for a grand total of 100 points. So all the true and false questions, for the most part, after you go over most topics for true and false, source from PowerPoint 15, I believe that's this one. Yeah. Most of the true and false questions source from lecture 15, which is applications. And you'll see that when we look through it. It talks about solar cells, LEDs, diodes, and stuff, and just general facts, which is to be expected. So then when we start with this, we can start at question 1. So has everyone here thrown an attempt at the practice quiz at this point?
I have.
I haven't yet, but
Yeah,
I
well,
believe you and I actually got the exact same score too.
yeah, wizards. That's how it be. All right. So the first things first. This was something that he touched on a long time ago in lecture as well, which is why I remembered the answer. But its built-in voltage of a PN junction diode decreases with higher temperature, and this is true. So if you look at the traditional formula for built-in voltage VBI, it's equal to KT over Q times ln of NA times ND over Ni squared. So that's the formula for built-in voltage of a diode at equilibrium. Now, if you look at that and look at only that and don't consider any other external potential factors that could factor in, you see that K is in the numerator of that. I mean, you see that T is in the numerator of that fraction. That, of course, is your temperature in Kelvin. If that temperature goes up, you would expect the voltage to go up, right? Because it looks like it's just a linear relationship. But as we see, the correct answer is it goes down. It's not a linear relationship. And the reasoning behind that is when you heat up a semiconductor, what changes? You actually, through that thermal energy, you generate more free carriers. And in this case, you generate more free carriers in both the P and the N side. So what that happens is it makes both of them have a lower resistivity. There's more free carriers, so it causes the Fermi levels to so the built-in voltage is like traditionally defined as the difference between Fermi levels. So the Fermi level equations will actually end up changing and they'll get closer together, closer towards EI. Therefore, the built-in voltage will lower overall. So the reasoning behind why the built-in voltage decreases at a higher temperature is because more free carriers are generated, causing the Fermi levels to grow closer together. Well, the quasi-Fermi levels, because there's 2 here. So does anyone have any further questions on that? Most of these questions in the true and false category are things you just want to memorize. Like this type of information, like you could sit down during the quiz and work it out if you really wanted to, formula-wise, but it's a massive waste of time. Because most of this type of information is something like, because obviously he can ask this question in 2 ways. He could ask, built-in voltage of a PN junction decreases with temperature or increases with temperature, and that obviously changes the answer. So you just need to know either the false variation or the true variation, and that'll immediately let you know the other answer when it comes to the 20 points, which should become like 20 free points. So just off the bat, built-in, and at the end of this, we'll put together all the formulas that we'll probably need for this test, which it turns out to be a lot more than expected because there's some like stuff from like straight up the beginning of the class that you need if you feel so inclined. So then question 2, the electric field in a PN junction diode is 0 under equilibrium. This is false. The whole point of a PN junction diode is that even under equilibrium, it still causes that depletion region at the center near the metallurgical junction point is what they start defining it as. I don't know if he's called it that in class very often, but on this quiz, they call it the metallurgical junction point, and they call it that on online resources as well. So where those two, where the N and the P type meet, it causes, it's at equilibrium, it's not under any type of bias, there's still an electric field because that depletion region exists. If that depletion region is no longer existent, then there is no electric field, but that depletion region forms an electric field that resists. That's what it's like when it's in reverse bias, it's because the electric field is causing a resistance towards the flow of current. And when in forward bias, the depletion region drops. When in reverse bias, it increases. So simply the fact that there is a depletion region of any size at equilibrium can prove to you that there is in fact an electric field. So it's not zero. It can't be zero when we're talking about these junctions. So there will always be an electric field, regardless of forward or reverse bias. The change is the magnitude of the electric field in terms of the depletion region, which will either decrease when it comes to forward or increase when it comes to reverse bias. And it'll stay at some constant value, which we have learned how to calculate when it's at equilibrium. So there is always an electric field in a PN junction. So this is always going to be false. Now this is one I didn't know because I didn't look over, which one is this? Yeah, I didn't look over the applications one beforehand. An LED will produce more light when forward biased compared to reverse biased. The answer is true. I said false. And I said false because I remembered a fact that wasn't exactly helpful here, but solar panels and LEDs are very, very similar. An LED is just a solar panel being operated in the reverse direction. If you were to put current onto the leads of a solar panel and pump current through the solar panel, it actually glows like an LED. So, and same thing, if you shine energy at an LED, it should generate a small amount of current. So they work off the same technology, hence the reason that like this is even something like these are applications. These are all applications of PN junctions. They're all the same thing to an extent. Like these two use optical, while this one uses like direct driven current. But an LED will produce more light when forward bias compared to reverse bias. So the reason I picked wrong here was because I remembered that when he was talking about solar panels, he said that when solar panels want to be operated in the reverse bias mode to increase the magnitude of the electric field. Because as I said earlier, when your PN junction is reverse biased, it has the greatest possible electric field to reverse the flow of that current, to resist the flow of that current. So here, I was like, oh, well, the most possible light. Well, it turns out that's not correct here, because what happens with an LED is I believe it's generating photoelectrons. So if you want to generate the most possible light, you don't necessarily care about the magnitude of your electric field. What you more care about is the magnitude of carriers that are traveling through that diode, through that junction. So the more carriers that are traveling, or like charge that's moving through these junctions, the more photoelectrons you'll produce. So if you want to produce the most light possible, you want the most carriers traveling through it. Therefore, you want it forward biased. Also, if you want to think about it, which is something I probably should have done, if you put an LED, when it's polar, because it's a polarized component, when you stick it in a circuit and it's operating and it's turned on, it's forward bias there. If you flip it around and put it in, it doesn't turn on, it doesn't produce any light. So there you go.
Oh, yeah.
That's an easy. I didn't think about it when I was taking this thing because I was just like, I got to get answers for this. But if I thought about it that way, it probably would have been easy. Yeah. So LEDs are operated in the forward bias mode when you're generating light. So just know that when you want to generate photoelectrons, you want the maximum amount of carriers flowing through that system as possible. Now this one was cringe on my part. Resistivity of the depletion region of a PN junction diode is independent of applied voltage. I should have obviously said false here. So the resistivity of the depletion region of a PN junction is not dependent on voltage. And we actually have the resistivity equation for that. It doesn't involve the applied voltage at all. So if you just look at the equation, you should be able to tell. But regardless of your applied voltage, resistivity doesn't change because resistivity is dependent upon the doping. It's dependent upon the doping of your two sides, your carrier lifetimes and Q. Because the formula.
So is it? I thought it was dependent on applied voltage.
Yeah.
It is.
It is, right?
It is.
Okay.
No, it says resistivity of the depletion region of a PN junction is independent of applied voltage. So it is dependent upon applied voltage. Sorry, I've been misspeaking because I misread this one. I said dependent instead of independent. So let me look at this again. Resistivity of the depletion region of the PN junction diode is independent of applied voltage. That is false. Why is that false? The depletion region, as I said earlier, didn't bring up again, at equilibrium, the depletion region is some set value that we're used to calculating. And now we know that when you put it under some applied voltage, whether or not it's forward or reverse bias causes that depletion region to either increase when you're under reverse bias or decrease under forward bias. Thereby, if the depletion region grows smaller, your resistance or resistivity will go down. And if your depletion region increases, your resistivity goes up. Because that means, over that area, that's a lot more, difficult an area for, let's say an electron to traverse when it's a big depletion region versus a small depletion region. So that's how that works. So directly, obviously we have a bunch of equations, but the easiest one to look at here is the depletion region equation with applied voltage, which the only change in the equation is where VBI is, you put VBI minus VA instead. So it's false. And it's false because it is in fact dependent upon applied voltage, because applied voltage will cause the system to no longer be in equilibrium, and it will either cause the resistivity to increase or decrease based on forward or reverse biasing. Don't know what this was. No question here. Just pick true and I was right.
So we have to pick true if it looks.
Yeah, if you see that question, pick true. If he doesn't have a question, pick true. All right. A good diode.
The same thing happened to me.
Yeah, a good diode offers high resistance in forward bias and low resistance in reverse bias. That is false. That is very false, and I'll quickly explain this again. But essentially, most of the true/false questions are all very, very closely related, because basically everything has to do with the reverse and forward biasing of either, a solar panel, an LED, a diode. So a good diode offers high resistance in forward bias. No, it doesn't. You want that. It's inversed. A good diode offers low resistance in the forward bias, because forward bias means you want stuff going through it. You want it to act like, essentially you want it to act as close to a wire as possible. And then when it is in reverse bias, you want it to get rid of as much current as possible. You want to minimize the amount of current flowing through it. So you want a super, super high resistance in reverse bias and a super, super low resistance in forward bias. Now, when it comes to diodes, we'll see that there's actually a pretty common number for that high resistance barrier that we're looking at. And I think it comes out to be like 3,125 kilo ohms, like in the mega ohm range overall, because it's you multiply that out or reduce it to regular ohms and it's in the million ohm range.
Wait, so to make sure I understand this correctly. So correctly, a good diode offers low resistance in forward bias and high resistance in reverse bias, right?
Yeah, that's what you want.
I thought that was actually mentioned in one of the lectures.
Yeah, so when you use a diode or an LED, when you use something that uses the PN junction in a circuit, because we're electrical engineers, we're pretty good at with circuit ideas in our head. When you put a diode, because a diode, you can think of it easily, if we're not going to talk any electrophysics, nothing like that. We're just going to talk about it in terms of just simple stuff that we know about in real life. A diode acts most understandably as a one-way valve. You put a diode in the forward bias in a circuit, it lets the electricity flow through it. When you put a diode backwards in a circuit, it blocks most everything that goes through it. Why? Because it's acting like a one-way valve. It's a polar component. It's what we call these things. Like you call an LED a polar component. That's why it's got a cathode and an anode, that kind of stuff. When a polar component exists, it's because either in this case, it only really works in one direction, or in some cases, if you backvolt it, it causes it to destroy itself, which is annoying. That sucks. Don't do that. When you reverse biased, I call it backvolt sometimes because I don't know why. It's physics teacher from high school speaking. But yeah, so an easy way to remember that is forward bias is for flow, reverse bias for stop, essentially. Another thing, like when I think of these in my head, I associate forward with green, I associate reverse with red, just reverse red. That's an easy way to remember it when it comes to the diode itself. When we're talking just about a basic diode, it can change in certain circumstances. Built-in potential in a PN junction diode is typically higher than the band gap energy. No, this is false. So we know that the band gap energy, like traditionally in silicon, is pretty big, isn't it? Isn't it like, I don't know the exact number, but I know that it's a little bit over 1 volts, volt to go from, I think it's to go from the valence band to the conduction band. The total gap between those two bands is a little over 1 volt. It's like 1 point something volts. That's just like, you can also use this in terms of you can use a formula to calculate this as well. But I know that like we can actually look up the band gap of silicon.
It's 1.12, I think.
Yep. In electron volts, and then obviously you have to transfer that. So it's 1.12 about. Now, knowing that, we've done a couple homeworks. Did I bring up one of my homeworks? Yeah, I have this one. I felt confident bringing up homework 4 because I got an 100 on this one. So if we need to reference anything, this one's good. He didn't grade homework 5 yet, so I have no clue. But so the built-in voltage, we've done a lot of calculating for built-in voltage, and a pattern that I've found is that the built-in voltage is almost always lower. In fact, it's almost always near like 0.7 volts or something's very, very close to that when we've been calculating built-in voltage. So the built-in voltage is just that, like, it's the energy difference between those Fermi levels again. So obviously, unless those Fermi levels are sitting at conduction band and valence band, there's no way it's going to be greater. It'll never, the Fermi levels will never exceed the values of the conduction and the valence band. Therefore, the built-in voltage can never exceed the band gap energy. It can only be at it, and it never will be at it, because I feel like there's probably no use for having your Fermi levels that far apart. So it'll always be lower. For our purposes, it'll always be lower. And most commonly, it'll hover around the 0.7 volt range. In a PN junction diode, the depletion region has higher resistivity than the neutral region. Yes. The reason behind this, the depletion region, as we said, the depletion region decreases under forward bias, increases under reverse bias. If you remember that, you know that, well, reverse bias is when you want the maximum resistance. If the depletion region increases, then it must mean that has some higher resistivity than the neutral portions, right? Because if the depletion region increases when your diode's supposed to have a higher resistance, obviously the increased depletion region is causing that resistance bump. But just in general, if you need to like do this mathematically, as opposed to like just intrinsically just remembering this like fact, the neutral region of either side, P and N, has comparatively a lot of free carriers. Therefore, it has a very, very lower resistance, has a much lower resistivity, versus the depletion region, which by its name is depleted of carriers because of a magnetic field that is generated by the union of the P and the P-type and the N-type silicon. The depletion region, by definition, is depleted of carriers. Therefore, it has a higher resistance than either side. So that's an easy one. That's why we call it the depletion region. It's depleted of carriers. So it has a much higher resistivity. All right. PN junction is forward biased if higher voltage is applied to the N side with respect to the P side. So I said false here. And this is a little bit of fudging on my part, but I have a decent enough explanation here. So if we draw, we've seen the PN junction before. I might pull up one of his slides where he has it doodled somewhere. Here we are. This is a good enough one, even though this is applied bias. So let's look at the question one more time. So a PN junction is forward biased if a higher voltage is applied to the N side with respect to the P side. So where was I? I was this one. So here they're saying a higher voltage is applied to the N side instead of the P side, right? A higher voltage is applied to the N side instead of the P side. So let's say we flipped this and the applied voltage was over here. Since we take, the change in potential, like let's say VA is 1 volt and ground is 0 volts, and we flip it here. VA, what did I say? What was my answer here? And I said false. Now think about it this way. This is just notation wise. Let's take VA to be a positive sign. Let's take ground to be a negative sign. Right here, if you were to do it like this, higher voltage on the P side, lower voltage on the N side, you're going to have a positive. You're going to have positive next to positive, negative next to negative. What's that going to cause? It's going to cause the net positive charges will be pushed towards the other thing, and the net negative charges from the ground will push together, and that'll cause the depletion region to decrease. Now, if you flipped it, like the question says, and had the higher voltage, the positive, on the N side, and had the lower voltage, the negative, on the P side, that'll cause it'll be negative, positive, negative, positive. That'll cause the charges to pull away from each other, thereby increasing the depletion region. And that is in reverse bias. If the depletion region goes up, you're in reverse bias. So this is electrostatics. And there's a lot, obviously there's math that you can do to solve this solid, but if you illustrate it like this, it's the same effect, but a much, much simplified version. Because if you put a positive point charge next to a positive point charge, they repel. Same with a negative point charge repel. So if you put negative, negative, positive, positive, it'll push the other ones together, decreasing the depletion region. You flip it like the question says, it pulls the depletion region apart, which means it's in reverse bias. Therefore, the answer, asking if it's in forward bias, it's not in forward bias here. Because the electrostatics here tell us that this is the proper, for that, like this description right here, the higher voltage, so it's gonna be positive, positive, negative, negative, is the proper use of the diode. This is what forward bias looks like. When it's in reverse bias, like the question says, you'd be flipping it, VA would be on the N side as it tells us. Therefore, the question is again false here. Does anyone have any more questions on that? That can be a little confusing. Like that that version or description, I would say.
Nah, I understood it pretty well.
All right, cool. I felt like it's a decent explanation. I was trying to figure it out how my high school teacher would describe it.
Wait, but if we can't take a quick detour, maybe it won't take. So I noticed. Go back to your last slide you was just on.
One.
Okay. So I mean, I just noticed it, but I never could understand the quasi-neutral. Could you
Where does
like
it
give
say
me a
that?
brief below? Like it's the first bullet point. The quasi-neutral. Like I don't understand. Is that something that we should know for this quiz?
Quasi-neutral.
I have
Oh
no.
yeah, okay. So here's what I think. So we're used to dealing with neutral N and P regions here, but here we can't say it's neutral because there's an applied voltage. So the applied voltage most directly affects the depletion region and the electric field and the diode and all that, but it's no longer a neutral system. But we can still refer to the P and the N type portions that aren't included in depletion region as quasi-neutral. We treat them as neutral because there's not much change that occurs in those specific portions of the diode, but it's not actually neutral by definition because there's an applied voltage across the system. So quasi-neutral is not something you're going to need to know for the test, but it's good to understand. Like I didn't even see that. It's good to pick it out. But yeah, quasi-neutral because the system is not under equilibrium. If it were under equilibrium, then it would just be neutral P and N regions. But quasi-neutral, yeah, quasi-neutral doesn't have any bearing in our actual calculations or anything like that. It's just a way to describe the fact that these aren't exactly neutral, but we can treat them as such because we're not interested in those portions. That was that. A solar cell will produce more photocurrent in reverse bias than forward bias. He said this in lecture, and this is true. Why is this true? Well, when you're in forward bias, your resistivity is low, your depletion region drops, your electric field drops. Because the electric field generated in a PN junction is generated to oppose a current flowing. If you have something operating in the reverse bias, you generate a larger electric field because that electric field increases because of the depletion region increasing, because we can actually calculate where electric field is directly related to the maximum electric field is related to, there's either the chunky equation you can use or the one I prefer, which is just 2 times VBI over the depletion region. So VBI is constant for the most part, even under an applied voltage, VBI is still a constant value. It's just slightly changed because of the VA being subtracted away from it. And in that formula, I believe that's what they do. They do VBI minus VA. So what happens there, though, is the depletion region, the electric field, if the depletion region goes down, let me check the rules here. If the depletion region decreases in magnitude, the electric field should go up. That doesn't make sense. Why is that the case? Here, I'm not going to explain this formula-wise. I'm going to explain this concept-wise like he did. So a solar cell will produce more photocurrent in reverse bias than forward bias. When you're in forward bias, your electric field magnitude is lower because you don't have to resist current, you're operating in the correct direction. You have the lowest resistance that you can have. When you're in reverse bias, the opposite is true. Your electric field increases to oppose the current and also has very high resistivity. Because of that, when you're in reverse bias, you have a bigger electric field. When we're interested in generating electricity, whether it be from a motor or from a solar cell, you want high magnitudes of changing electric fields. Well, the best way to have a changing electric field is have an extremely high electric field generated every time a photon hits your material, and then drop back down to zero. And that change in electric field will generate more electricity than if you were to operate it the other way. Because then, the more change in your electric field, whether it be a motor or a solar cell, should generate more energy, more electricity or current. So in his lecture, he touched on this point very briefly. He essentially just said that like you want a higher electric field when you're generating electricity. It's basically all he said there. And I'm sure that if we were to go, is this the applications one? No, this should be it. Yeah, why is a PN junction a good solar cell? Built-in electric field, where are you? Here's some equations for solar cell. Oh, well, he didn't talk too much about it, I suppose. He didn't write too much about it. He spoke about it. So for this one, since this will be a true or false question, there's no math that he can have for us with regards to this question. Like there's no math confirmation. This is definitely going to be a type of true or false question. So in this instance, just no solar cells are designed to operate in the reverse bias. All right, so question 11. Which of the following is true about the energy barrier that keeps electrons on the N side and holes on the P side? Well, it decreases under forward bias and increases under reverse bias. This energy barrier that we're referencing is that electric field that generates or is created by the depletion region and by the diode itself. So as we know, the electric field goes down when the depletion region goes down and vice versa. So there's that. So that's a pretty quick one. This is our first actual multiple choice question, by the way. I believe all the true or false, that was all 10 true or false. And now we're going on to the 20 multiple choice. So for the first multiple choice question, that's essentially it. It's just asking, it's asking whether it's yet again touching on forward and reverse biases here. And all it's saying is, when does your electric field increase or decrease? And we know that it increases under reverse, decreases under forward. So that's how I answer this one. Now this is one that I messed up, but it's actually, if you had all your formulas in front of you, you could eventually find the answer. So which of the following is true about the diode regarding the diode saturation current? The correct answer is higher the majority carrier lifetime, the higher the majority carrier lifetime, lower is saturation current. I don't believe that's correct grammar, but I don't really mind too much. He has a formula for the diode saturation current. Here it is right here. J0 is normally, he gives us right here, it's normally just given to you inherently as a number. But there is in fact a formula for it. And it's a really chunky formula, considering that it's normally just a number we're given. You don't really think about how much it takes to get you to that number in the first place. So this is something that you can calculate normally at the beginning of the question easily. Same here as a constant. Now your DP and your LP are not that. Those things are given to you. We're aware of that, like diffusion length and the diffusion coefficients. If you look at this, we know that diffusion length is what? That is the diffusion length is the square root of D of the material of either P or N times the tau of P or N, correct? If we remember that from MCDE. I have that written down right over here. Yeah, diffusion length is equal to the square root. So let's say it's Ln here is equal to the square root of Dn times tau n, where tau n is everyone remember? Tau n's the majority carrier lifetime, right? Like the tau values are the majority carrier lifetimes, if I remember correctly. Yeah. Okay.
It's the minority.
The minority carrier lifetime. Yeah.
Right here.
So, yeah. So the tau n,
Most of it, except
where do you
for
say
the-
it? What is he asking here?
No.
Okay. Did you carry it around all day?
Yeah.
Yes, it's right there.
So the formula was right here.
Matter.
So looking at this formula,
Rattle. What's the matter?
Nothing really.
Okay. You got this quiz tomorrow?
Yep. Oh no, I know what it is. I forgot to get. I forgot to get my. I forgot to go see testing services. So I don't know if the test is in there.
Oh, don't you have a cord?
I muted him. All right. So now, yeah. All right. So, because obviously this is recorded, so we don't need his personal stuff if there were to be any, being blasted. So we look at this formula. So we know what DP will be given, and we know what ln is. So the minority carrier lifetimes are going to end up in the denominators of those second terms across the sum. So your LP and your ln is going to include two separate minority carrier lifetime values. They'll probably be the same, assuming this is a symmetric. If this is a symmetric PN junction, then they would be the same. Otherwise, they wouldn't be, because you'd have to calculate each of them separately. So now if we look at this, so your ni squared over nd and your ni squared over na, that's some number. Your d some number over the square root of d tau n. So the higher your d tau n is, the lower your current will be, right? Because if the denominator of something is bigger and bigger, the lower and lower the overall number is going to be. If you divide 1 by 2, it's 0.5. Divide 1 by 4, it's 0.25. It gets lower and lower and lower. And that's the same for both terms being summed. So across the board, minority carrier lifetime, as it increases, will decrease the total sum. Therefore, higher the minority carrier lifetime, lower the saturation current is the correct answer. And that's because of the formula right here. So this is one we're going to put on the formula sheet because this is important. We probably won't need it for anything but this if you want to confirm, because otherwise he says it's just a number for the most part. And so far he's always given us the number. But just in case, if you want to confirm it for yourself at any given time, you simply have to rewrite this formula with LP and LN subbed in from the MCDE equations that we're aware of, which is a square root of D n tau n or dp tau p. And then you can use that to know that, okay, higher the minority carrier lifetime, lower the current, or lower the saturation current will become. So that's why that's the correct answer. So if the current through a PN junction diode is 1 milliamp, which of the following statements is true? So I saw this assumed diode saturation current is this and no reversal breakdown. I don't know what that means at the time. So I was like, it doesn't matter to me. All I know is that 1 milliamp is a lot of amps relative to a system like this. If you're operating a diode in the reverse bias, you should be nowhere near a milliamp. A diode is designed, or a PN junction diode, same thing, is designed to minimize the current flowing and the carriers flowing under reverse bias. And because of that, if you're under forward bias, you can expect to see currents in the range of milliamp higher and higher, like you see through a wire in a circuit. Most circuits we're used to working with, like let's say you're trying to power an LED, you stick a resistor on the LED, you're going to see currents in the order of milliamps. And that's because LEDs are operating in the forward bias. It's a PN junction. There's a reason LEDs blow out so easily. It's because they can only take so much current. You can't pump 2 amps through an LED. And this PN junction is limited to 1 milliamp. So that's perfectly within the range that's acceptable for forward bias operation of the system. So you can tell that this is forward bias just because that's really big. If this was operating in the reverse bias, it would probably just explode by then. That's pretty well, probably not. It probably wouldn't explode. It just wouldn't let anything through. It wouldn't let through nearly as much as 1 milliamp. And if it were letting through a milliamp, it probably had broken down and is no longer functioning correctly. So
What I did to solve that problem was the current density equation.
Which equation?
The conduction current density. It's J equals J naught parentheses E to QVA over KT minus 1.
This one?
Oh, yes, that one.
Okay.
JD would be 1 milliamp, J naught is 1 nanoamp, and you just solve for V.
And if V and then what? So because of the sign on V, you can solve or what?
Yeah, you when you take the natural log to get rid of the exponential, and then you just manipulate it to solve for V, and you get like 0.35 volts roughly.
Yeah. So let us do a little trick. So there's
Okay.
obviously, so now we have a mathematical method to solve for this as well, which is good. I was only able to get this right. So I didn't do any math here. I was able to get this right simply because I'm used to dealing with diodes. So I'm aware that this is kind of ridiculous for the reverse bias. But now we have a method to solve for this mathematically. So let's use this equation real quickly and see what we get out of it and see how we can use it to tell us if it is operating in the reverse bias, if that were the case. KT minus 1. So as you said, JD is going to be 1 times 10 to the negative 3 amps. J0 is going to be 1 times 10 to the negative 9 amps. 1 times 10 to the negative 9 amps. And then you have your EQ, which did you use Q as 1 electron volt, or did you? Yeah, you definitely use Q as 1 electron volt, right?
I said Q was 1.6 times 10 to the minus
Oh.
19.
Well, I guess since you're using ln, it doesn't really matter, right? Well, yeah, you should use it that way, I suppose. Because traditionally, I see since the E drops away here, but normally if you're working with like Euler, like a Euler function like that, or E to the X.
Oh,
and
I see what you mean.
And you have like a
Q over K.
Yeah, Q over KT or
Yeah,
whatever.
I did use 1 over 0.026.
Oh, so okay, so you did use it in electron volts then. Because Q in electron volts is simply 1. So you did 1
Yeah.
over 0.026. Okay, cool. And then you did minus 1 here. So obviously your first step, or the first step I would take, is I'd divide the nanoamps over 1 times 10 to the negative 3 divided by 1 times 10 to the negative 9. I did 19th like a genius. Divided by 1 times 10 to the negative 9th. It's going to give you big boy number, which happens to be, looks like 1 million, because that's going to produce 1 times 10 to the 6th. 1 million. And then now you have 1 million is equal to that inner quantity of the parentheses. You can add 1, so now it's 1,000,001 on one side. 1,000,001 on one side is equal to E V over 0.026. Take ln of both sides. Ln of
I got
both.
like 1.35.
Yeah, so you'll have ln of big number, and then ln of big number just becomes something like 13.8 ish is equal to V over 0.026. Multiply that across 0.026. And what did you say you got as your voltage?
The pod voltage is 1.35 volts.
1.3. I got 0.36 volts.
Did you forget? You probably forgot to add 1 to both sides. Did you do that?
Yeah, he did that when he added the million.
Yeah, because it's 1 million on one side, right? So it doesn't change by
yes.
much.
Essentially, my formula was 0.026 ln of J over JD, and then I just added 1 to that result.
JD over J's of J naught, right?
Yes.
Okay, so that 10 to the negative 3rd divided by 10 to the negative 6th produces 10 to the negative 9th produces 10 to the 6th. So then that is 1 million. And then now you have your EQV over KT minus 1 on the other side. As you said, you add 1 over. So 1 million plus 1 is just 1,000,001. So essentially you could go without adding that 1. It doesn't change the answer too much. Because then if you take ln of the big number and ln of the other side, you get 13.8.
Oh, I see what you did.
13.8 is equal to V over. So here's the question. So did you accidentally did you do 0.26 instead of 0.026, Or did you do
I
something
did,
else?
I did, 0.026.
Did you get a, so right before you solve for V, did you do 13, was it like 13 point something is equal to V over 0.026?
What I did was, well, I see what the difference is between you said 1,000,001, which was that you adding that one to that other side.
Yes.
I didn't do that. I said a million and then times LN times 0.026. Then I just added one to that result. If that
Well,
makes sense.
so you did, so your function was ln of 1,000,000 is equal to like E, or is equal to ln E minus 1.
I think so. If I understood you correctly.
Yeah, so if you were to do it that way, it would be, you'd have to raise the 1 to ln as well. And ln of 1 is 0. So as I said, it's negligible. So the 1 would drop out there as well, and it should still leave you with 0.36 volts in this instance. So you just did an algebra error there. It's not a big problem. Yeah. So the reason I wanted to run through that is first off to demonstrate that it is possible to, solve this mathematically with this equation. This is I think this is this drift? JD. Yeah, here's what he tells you right now. But yeah, this is what I was gonna say as well. So right here, forward bias, your voltage is greater than 0. Reverse bias, your voltage is less than 0. So right at the beginning, before I worked this out, I asked you if based on the sign of the voltage, you could tell whether or not it was forward or reverse bias. And it looks like that's exactly what that tells you. If the sign is negative, you're working with a reverse bias system. If the sign is positive, you're working with a forward bias system.
Oh, so since it's 1 milliamp and it's not negative 1 milliamp or something like that. So
in this case, you can't tell off of the current immediately. I don't think. But you might be right in that case. It might be possible because obviously we would have to work an example where it's in the reverse bias to know for sure. But just in case, when you come to these types of questions, since these are multiple choice questions and they're worth 4 points, it's worth the time to run through and do the calculation. It's pretty easy, pretty quick, just to confirm with you. So
and just plug it into the equation we just did.
Yeah. The JD equation, and plugging that in, of course, will tell you
I was going to say, like, practically, a power supply can't produce negative current. The negative current just means it's just going in the opposite direction of your calculations.
Exactly correct. So if he were to give you, a negative milliampere, I'm pretty sure, yeah, that should immediately. Would it though? Well, if you give him a negative current, we'll know immediately that because it's going to be a negative divided by a positive, and that's going to become, negative 1 million. The problem with that is ln of a negative is a no-go. So you can't use the formula there. So I'm going to go back to his PowerPoint real quick and see what he means here. Less than.
So wait. So I missed out on that. So where exactly did you plug in the 1 milliamp? You plug that. Go back up to the equation.
1 milliamp is right here.
JD.
JD. So let's go back to the question. If the current through a PN junction is 1 milliamp, so think of the JD as applied current. And this is the diode saturation current, which is J0. It was given to us here. Boop. So essentially, it looks like there's no change to the formula. So he's telling you in reverse bias, J0 is just going to be negative J0. So that's that, I suppose. So you can know right off the bat that if you plug in this equation and it produces, a positive J0 times this quantity, which is essentially, yeah, that's what in here he's not doing what we did. He's not reverse solving it because he's solving for JD as opposed to like solving for V. Oh, okay, so now I understand how the formula works. So in this instance, the formula could not work the way we wanted it to if he gave us a reverse bias system. Because then we would have a negative value for ln, and that's a no-go. So when traditionally
I would-
working,
I was gonna say I would just assume we would just I would just assume we would take the positive value of the magnitude.
I would hope. But if he does give you, because as Roosevelt said, the trick there is if this was in fact, negative 1 milliamp, what's the reference, right? The only reason you would need to know that that is negative is if it's going in the reverse direction of the expected polarity. So if you were to be given a negative 1 milliamp, you should be able to immediately deduce that this is in fact being operated in the reverse bias. Otherwise, why would he give you a negative sign? Because there's no implied, like when it comes to a normal component, there's no implied polarity. But in this case, there is an implied polarity. So if he does give you a negative, that means it's reverse bias. But when using the equation traditionally, when you're solving for the value of JD, based off of your voltage, you'll be given a voltage value or something. If the voltage is greater than 0, it's going to be forward bias. If it's less than 0, it's going to be reverse bias. So you can tell based off of a given voltage value as well, which is what we were doing when we were back solving it. All right, so that was that one. All right, assume that the N side doping of a PN junction is twice the doping density in the P side. If the built-in voltage of the diode is 0.9 volts, which of the following is correct? Okay, so now we are looking at, what was it asking about? Oh, it's asking about the potential. Okay, so this is the ratio of the voltage that you have at a given point. So this all has to do with the ratio of the depletion regions because of the doping densities. So there's two ways to calculate the depletion region. There's the big overall function with the square root, or there's the ratio version, which you still need to calculate the actual depletion region value in order to use the ratio version. But the ratio version is the sum of Wn plus Wp. Wn is Na over Na plus Nd, and Wp is Nd over Nd plus Na. So right here, we see the doping density on the P side is half that of the N side, or the N side has twice the doping density of the P side. Therefore, your Na is equal to, or your Nd is equal to 2Na, right? So that's what we know right off the bat. So using this ratio, we can say, let's calculate. So this is asking the potential at the metallurgical junction point. So it's starting from the P side going over to the N side, or vice versa. You can pick, really. It's not going to change the answer. So the PN junction, and oh, here's what's telling us where to start. We're assuming we're starting at the P side. The P side starts at 0, and then it's going to go up. So we're going from P to N. Knowing that, we want to calculate the P side then, the P side's ratio. So Wp, as I just said, is equal to Nd over Nd plus Na. Okay, well, we said Nd is equal to 2Na over 2Na plus Na. Okay, what does that give us? That gives us 2 over 3. 2/3. What's 2/3 times 0.9? It's 0.6.
Hey, so is that formula actually somewhere in the slides?
Really long time ago on the equilibrium, like the beginning slide stuff. Let's see. Right here, these ones. As I said, you still need to calculate the depletion region if you're actually trying to find the proper value of Wn or Wp, but you don't, in this instance, you don't need to, because you simply want to know the ratio, because that's what these are. These, when you sum, because look, it's Wp plus Wn is equal to the big boy formula, which this is what you want to use if you're solving for this directly. But if he ever asks you, which he's asked us before, solve for how much of the depletion region is on this side or this side, you need to solve individually for the portion or the ratio of the depletion region that is present on each side.
Are you solving the formula just at like the W DEP isn't there, like just X that out, or it's still there?
You didn't, when I just used it there, you don't need to use that. You don't need the WDEP there for either of them for the question we just did, because it's not asking about the depletion width. It's asking about the potential. The depletion width, if we look at, here's a great illustration. This is what he's talking about here. So the depletion width starts here. So this is what it looks like in the diode. Now there's a charge. So this is asymmetrical. So looking at this, you can tell that the P is higher doped. It has a higher doping density because, as we know, density is, how much of something is present in a given area or volume traditionally. So looking at this, the doping density on the P side is higher. Why? Because the depletion width is smaller and it has the same charge value. Like if you look, it has a higher magnitude of charge and a lesser magnitude of area. So you can see that the electric field is across the board here, and this is why he relates all these all these equations or whatever together. So you have a peak of electric field, and that peak is where the junction actually appears. So that's another thing. The peak or max value of electric field occurs at the metallurgical junction point, whichever you like to call it. Your WP and your WN region is what separates these portions. And at the peak, there's also, your voltage. And your built-in voltage is what this is going to vary between, like your magnitude. So you're going to have your lowest voltage, upper voltage. That's what this whole thing is. That's what built-in voltage means. So when we start here, this is a higher doping density because it has a higher magnitude of charge and a smaller magnitude of area. And this one has a lower doping density because it has a lesser magnitude of charge, but in more area. So if you were to actually calculate the areas of both of these figures, they should be equal, I believe. Yes, if you were to calculate the charge, I believe it's supposed to be equal there, because this is an equilibrium. So knowing this and how the fact that these WPWN is what directly affects this relationship across the board, the doping density ratios is what directly affects this relationship down the line for all properties of our PN junction. So here, and this is essentially the exact question that was asked of us, because it said P, assume potential of the neutral P side is 0. So we're assuming that we're starting at 0 on the P side, which that's what we're doing in this question. You start at 0. Okay. So what do you want to do now? Well, you want to calculate the width of WP. Okay, you calculate the width of WP. That's what we did. You calculate the ratio of the width. We don't need the exact width here. We just need the ratio of the width. Because overall, the width of this whole thing is, for this formula, for the purposes of this math, is 1. And we only need to calculate the ratio, or how much of that 100% is taken up by the P or the N side. We calculated that in our question, P is less doped. N is doped twice more, like 2 times Na. So using that, you calculate that P value, and we came out 2Na over 3Na, cross out your NAs, is going to be 2 over 3. That's 2/3, or like 0.666. So what you do is you simply take your ratio at your given point. It's asking at the junction point. So that's why we start at 0 and calculate up until the junction point, which means we're calculating WP. So you calculate WP, it happens to be 2/3. You multiply 2/3 by your built-in voltage, which was given to us as 0.9 in the question, because that's what the difference in potential is, as illustrated in this figure. When you multiply it there, it's going to give you the voltage at the junction point. If you go down the line, it's going to give you the voltage at the junction point, which is some intermediate value between 0 and the built-in voltage, which for our cases was 0.6. So super long-winded explanation, but in terms of actually performing the calculations here, it's simply the ratio of the side it asks you to start on. You know what side it asks you to start on because it'll tell you it's 0. That's all it takes for these ones. And then you multiply it by the voltage it gives you. Now, he could be tricky, and I feel like he might do this because he's done this in the past when it comes to fill in the blank or multiple choice questions, where he'll have numbers and answers that are carrying through several questions. And if he does do that, that means that your built-in voltage is what you're going to carry in for the solution to this question. Maybe he won't give you 0.9. He'll just tell you to calculate it, and you'll have to know to use your built-in voltage from a previous question. But here he just gave us the value, which is great. So that's how that works. So for these ones, when you're finding the potential at the, the junction point, it's simply the ratio of the depletion region of either the N or the P type, whichever side it told you to start at, times the built-in voltage. And it'll tell you. And that'll give you your value, which is 0.6. Is there any more clarification that might be needed for this type of question? Like formula-wise or anything?
Pretty good.
Okay, cool. All right. Question 15. Assume that the N side doping density of a PN junction diode is twice the doping density of the P side. Okay, so another something like that. If the total depletion width is 300 nanometers, which of the following is correct? So now we have to use these functions the right way, which is we're no longer just saying that the W depletion just drops out. This time we're given it, so luckily we don't have to calculate it because that'll take some time. But we're given it, so we have to use it this time. So this is the same process as last time. You're simply calculating the ratio again, but this time you're carrying through and calculating and multiplying that ratio for both sides times what you have. So if we look at this, the N side doping density is twice the doping density in the P side. So this is the exact same thing here. The N side doping density is twice the doping density in the P side. So we know that the P side has a ratio of 2/3. Well, what's 2/3 times 300? It's 200. And then whatever's remaining is your opposite side. So this is the same exact principle, but multiplying by a different value. It's multiplying by the depletion region here. But because this figure that he has is super helpful, like this is something that like when you start the lecture, you're like, oh, that's cool looking. But this is actually like, this is the whole principle of like 6 of these questions in a row. The fact that the depletion region is basically all we care about when it comes to the PN junction. We don't care what happens here. We don't care what happens here. This stuff's explainable by the stuff we did right at the beginning, like chapter 1 stuff. That's easy stuff. We want to know what's happening in this area of change, in this area of flux. And this is what we want to know. And this is like the fact that the depletion region affects everything across the board. All the values are dependent upon depletion region across the board, minus VBI, which is intrinsic to the material. So that one's that. So any questions on how to do this one? It's the same thing, same exact ratios. And this time you just multiply by a different number instead of the built-in voltage, the depletion width, but you'll get the same thing. This one is just straight plug and chug with the formulas.
Wait,
Yes.
go back to it. So you said straight. So we're using that same formula we used for the last question. For that
Yeah,
question.
this. So remember last time, instead of using this, we simply just took this ratio and multiplied it by the built-in voltage.
We just took 2 divided by 3 and multiplied it by 0.9.
Yeah.
Right.
Yeah. So instead, for this question, you're using both of them, even though you technically only need to use one of them because So you could pick either one, whichever one you feel more comfortable solving. You'd solve for the ratio. So in this instance, since WP is 2 times smaller, it's going to be bigger. Because remember, if your density is higher, you have a smaller portion of the depletion region in terms of actual area when you're looking at it. Because if you're less dense, you can see these things are more separated, less dense, more dense. So the higher density has less area, so a smaller ratio. So since we're calculating on the P side here, this is going to have 2/3. This is going to have 1/3. 1/3 times 300 is 100. 2/3 times 300 is 200.
But was that given it like in the last problem we kind of knew because you said that like NA was double. So in the problem.
Yeah. This one has the exact same problem statement. Assume that the N side doping density of the PN junction diode is twice the doping density in the P side. They start identically, and then the second sentence is what's different across these two questions.
Okay. It's just that 1/3 part that they're.
Yeah, so it's literally the exact same process, but instead of multiplying our ratio by the built-in voltage, it's being multiplied by the depletion width.
All right, gotcha.
Yeah. All right. Question 16. Which of the following is true for the forward biasing of an ideal PN junction diode? So this is what we talked about earlier in the true or false portion, but this time you made it into a multiple choice question. So which of the following is true about the forward biasing? The P side is connected to positive voltage and the N side is grounded. So remember, when we want to operate a PN junction in the forward bias, that means we want to decrease the depletion region. So the traditional electrostatics of the PN junction I don't know where I put it. Yeah, this is good. This one's good enough. We'll just use this one. So the traditional electrostatics of the is this even right? Where did I put it? It's much better figure somewhere else. Where did I put it? This is just a bunch of questions. It has to be here, right? I think it was, yeah, this one. This is the one I want. All right. So this is the traditional electrostatics of the p-n junction that we're used to dealing with. One's got the positive side and one's got the negative side. So he's asking here, which of the following is true about the forward biasing? So in forward bias, you want to minimize that depletion region. So if you want to minimize the depletion region here, you want to operate it like this. This minimizes it. This is operating on the forward bias. You have a plus plus, a minus minus, because the plus and the plus are going to repel and the minus and minus are going to repel, forcing those two center bits closer together, causing the depletion region to decrease. Overall, gives you the net effect. The P side, which as we can see right there is positive, is connected to the positive voltage, and the N side is connected to the ground or the negative voltage, the grounded voltage. So you have a positive, positive, negative, negative, and that causes it to decrease. And it's the same exact principle as earlier. Where is that hiding? This one. This is the same question. This is the exact same question, just asked a little bit differently. One of them's asking you to actually explain. This one's asking you, because this one could trick you, right? Because it gives you more things. Okay, like none of the options is always like something people like to pick if they're kind of lost. But for the most part, it doesn't seem like he makes these the answers all that often. Polarity of voltage connection does not matter. That's very wrong. We're operating with all the components that we're dealing with here are all polar components. The polarity always matters at this point. And then here, this is the exact inverse. This is him operating it in the reverse bias, because this time it's going negative, positive, negative, positive, negative, positive. Yeah, he reversed it because that's going to draw the central bits apart, causing depletion region to increase, thereby making it operate in the reverse bias. So that's what this question is all about. It's the same exact principle as the one earlier, just being asked in a slightly different way, but it's the exact same rule. All right. The magnitude of the electric field in a p-n junction depends on, all the options correct here, right? So the electric field's a big, big formula, and it's derived from both the built-in voltage and the depletion width. And the built-in voltage and depletion width. So we can start off with built-in voltage here. Built-in voltage directly varies based off of, as we were aware from earlier, temperature. Temperature affects the built-in voltage a lot. So we could put temperature on that list. NA and ND are present in both the depletion width formula and the built-in voltage formula, not to mention that the depletion width formula incorporates built-in voltage as a parameter. Therefore, anything that affects built-in voltage will affect depletion region, which will ultimately affect the electromagnetic field. So we see NA and ND, so they're your doping densities. So we have two parameters so far. We have doping density and we have temperature, both parameters that matter. And now we get to applied voltage, which is a bit tricky, because if we were working with only the formulas and the equilibrium that we're aware of using, like the ones I just listed, the equilibrium formulas, we wouldn't immediately know if applied voltage matters. But applied voltage obviously matters. And we know that because the formulas for applied voltage slightly change. And the only thing that changes when you apply a voltage, where is it? Is this applied voltage? Yeah, this is under bias. Here they are. Here are your changes. All your changes. Look, anywhere where VBI was, you tack on a negative VA. And here's your electric field. This is all you need to know. Look at this. VBI affects it, thereby temperature and doping density are parameters. And look, VA is right there. It's another parameter. Therefore, all of these parameters are present and have a function, and they have a effect on the overall electric field's magnitude in a p-n junction. Therefore, all the options are correct here. So that's just a game of either remembering the fact that magnitude is dependent, or the magnitude of electric field is dependent on all those parameters, or you can look at the formulas if you need a refresh on the test. And you can immediately know after looking through the formulas that yes, all of these things are present and have a hand in affecting the overall value. of the electric field.
What's the question? But what was question 16 again? Hold on. I just forgot. So
Yeah, this is the
Okay,
that was the copycat question from the true or false section. Now we get this question 18. The depletion width of a PN junction diode under equilibrium is 1 micrometer. Which of the following statements is true? The depletion region is equal to 2 micrometers under reverse bias. So I'll tell you why I'll tell you why I knew not to pick the other ones instead of why I picked this one. Because here, there's no math you can do. This is a full-on concept question. There's like just given the depletion width, if you're just given that number and nothing else, there's no way you'll be able to calculate any other numbers. You'll need applied voltages, like you won't be able to. So this is all concept. So first off, the depletion region, 1 micrometer under forward bias. So when this is under equilibrium, when there is no applied voltage, therefore no bias, it is 1 micrometer. And we know that under forward bias, the depletion region decreases. Under reverse bias, it increases. Okay, well, this is under forward bias and it's the same number. It didn't change at all. That doesn't make sense. That's a wrong answer. Now, the depletion region is 0.5 micrometers under reverse bias. Well, we know that under reverse bias, the equilibrium depletion region should go up. It went down. That's a wrong answer. Next one, the depletion region is 2 micrometers under forward bias. Well, we know that under forward bias, the equilibrium depletion region should go down. That went up. Wrong answer. And the last one, the depletion region is equal to 2 micrometers under reverse bias. We know under reverse bias, the depletion region goes up. It went up. Checkmate. That's the right answer. That's all it takes with this one. No math. It's all concepts here. Are there any questions as to why that's like the answer? Or
can you explain it going up? Did you already explain it going up and down?
Yeah.
Certain.
Yeah. So that's what this question is. These questions are super closely related because this question and that previous true and false question all operate on the same principle here. When you're operating in forward bias, your charges are able to flow and the depletion region decreases and the overall resistivity of your PN junction diode goes down in that direction. When you operate in reverse bias, the reverse is true. Your depletion region increases in size, your resistivity shoots up, and you almost have no flow. Very little current can get through, if any at all.
Okay, cool.
Now, so the reason behind that is we've looked at this because this is all when it's under bias. Equilibrium stuff doesn't change. That's a constant. Your depletion region under equilibrium is just going to be a number that will not change. But when it's being put under a bias, this all has to do with electrostatics. Obviously, everything is electrical engineering is going to just come down to the physics of electrostatics at one point or another. And right here is a perfect example of this. This is when it's under forward bias. It's under forward bias because you have, so what you can do is you can replace your VA with a positive, your ground with a negative. If you have a positive, positive, negative, negative, we know that like signs repel. So your positive is going to repel away from your positive, negative is going to repel away from your negative. What does that cause? That causes those negative and positives at the depletion region to push closer together, thereby causing that depletion region to decrease in size. That's why the forward bias decreases the depletion region and lets stuff flow. Now, if you had negative, positive, it does the reverse. They attract to each other. That means the ones at the center get farther apart. That means your depletion region goes up, and that means you're operating in the reverse bias. So it's the same electrostatic principle across the board for here. Well, technically for every question, that's when it's under bias, it's the same electrostatic principle. But that's just like why this is like how you're able to answer that. If you know that principle from the get-go, this type of question will be a piece of cake. All right, question 19. I got this one wrong because I'm a numbnuts and I read it wrong. Consider symmetrically doped. So symmetrically doped. Be happy when you see the word symmetrically doped. That means everything gets a lot easier. PN junction diode. What is the resistivity exactly at the metallurgical junction point if the diode is forward? I read that as reverse bias because I'm a dummy. Is forward biased with 0.5 volts. Assume mobility of both electrons and holes is 1000 centimeters squared per volt second. So as you can see, I picked a big number, and here's the kicker. I picked the wrong big number. if this was reverse biased, I'm pretty sure it's still the wrong big number. It should have been in the mega ohm range and not that range. So either way, across the board, I'm just wrong on this question. But if you look at it, we know that under forward biasing, the resistance is extremely low. So right off the bat, that lets you eliminate two answers. Anything in the kilo ohm range, you know, and this isn't even just kilo ohm range. This is like the hundreds of thousands of kilo ohms. It's kind of
But-
ridiculous.
Since the resistance, okay, y'all hear me?
Yeah, I can now.
All right, so since the resistance is low, so the resistance is low and forward bias. So how is that able to cancel out? You said the mega ohm stuff.
Yeah,
Like,
so
how does the resistance deal with the number being big? like-
so resistance. So this is asking, is this asking for resistivity? Yes, so resistivity. So I keep saying resistance, and that's technically wrong. We mean to say resistivity, but when you're in the forward bias, your resistivity is low because your depletion region is smaller. So when you think about it, when you want current to flow in a diode, you want very little resistance. You want it to be as close to a wire as you can for the most part. Because of that,
What I mean, be sm-
Hmm?
So does that mean it's gonna be a small number?
yeah, it's going to be a
That-
very, very small number.
All right.
It's going to be in like that range of the correct answer range, which is, you know, no kilo ohms. It's like 10 or 20 ohms. Now, the hard part is selecting between those two answers. Because as I said, if you read the question right, and you see it says forward biasing, you immediately are able to, you know, get rid of those huge numbers, those last two answers. But because of that, now you're still left with two answers, that being 20 ohm centimeters, which happens to be the right answer, and 10 ohm centimeters, which happens to be the wrong answer. So let's look at resistivity. What's the formula for resistivity? Well, it's just, you know, the weird looking P that I forgot the Greek name for is equal to 1 over Q times mu N times your ND plus mu P times your NA. Okay, so we were given all those numbers. We were given NA and ND is equal to 10 to the 17th. We were given both mu values are equal to 1,000 and Q is a constant. So let's calculate this out. It should spit out 20, but I will confirm that for you momentarily. So if we do 1,000 times 10 to the 17th, and they're both all the same, so that's just going to be times 2 here. Times 2 times, you know, 1.602 times 10 to the negative 19th. Going to give you that number, right? 1 divided by that number. No, that can't be right. That's cringe. Oh, I'm forgetting something. There's a relationship with the forward biasing, isn't there? Yes, there is. I feel like I'm using the wrong formula for this. Let's look over and find the right formula then, shall we?
You're gonna want to use n's equal to p, which is equal to NIE to QVA over 2 KT.
All right, say that one more
And then-
time, because that's definitely the right. That's definitely the right formula here.
You're gonna want to use n's equal to p, which is equal to NIE to QVA over 2 KT. And then when you get n and p, you just plug it into the resistivity formula.
That's what I'm missing there. Yeah, so he has that relationship. Obviously, the voltage is an applied voltage, so why am I on the equilibrium slides? Here we are. These are review questions. This one, right?
Yes, that one.
This is the equation. All right.
But,
So that was the
but
mistake I was making there.
instead of multiplying n and p, I just said n's equal to p.
Mm-hmm.
Wait, so
Which-
solving this equation right here is gonna give us the 20?
Yeah, so there's two equations you end up using here. So the mistake I just made was using the ND and NAs that were given as 10 to the 17th in the traditional resistivity equation that we're used to using, which if this were under equilibrium would have worked, but it's not under equilibrium. This is under an applied voltage. So in the traditional resistivity equation, applied voltage does not factor in, therefore it's not going to be right. This is the equation you need to use, not to solve for resistivity, but instead to solve for your ND and your NA values, which as stated are going to be equal, as he just said, is going to be N is equal to whatever. So what ends up across the board is you can say N is, it would be the same thing as saying N squared or P squared, essentially. So you do that is equal to Ni squared, which is 10 to the 20th, times E, and then you can do probably VA over 0.026 because you can set Q as 1 electron volt, hopefully.
So was VA 0.5?
0.5 here. So you would solve across the board. You could do 10 to the 17th times 10 to the 17th. What is it even solving for here? No, you're right. So it wouldn't be that. What you'd do is you would set those and leave them be. You would leave them be and say nx squared or px squared, because they're set equal to each other, it doesn't matter, is equal to the number you get on the right side. And then you would square root the number on the right side. And that would give you your value of N and P, which you would then take back and plug into your resistivity equation in place of ND and NA. And that will give you your 20 ohm centimeters resistivity. So the trick with this equation or this problem is knowing to set N of X and P of X equal to each other, which means it's going to be N of X times N of X or P of X times P of X. So you can take either one and have it be N of X squared is equal to whatever this number works out to be on the right, square root both sides, and that'll give you your N of X and your P of X values, which you can take back and plug into the traditional resistivity equation. And then that will give you the resistivity of 20 ohm centimeters. So when calculating for resistivity in a biased system, we want to use this equation to solve for the majority carrier densities. Boop. All right. And now if the current through a PN junction is 1 milliamp, what is the applied voltage? Well, we did this earlier using, was it in this? I'm pretty sure it was probably in this. It's the current formulas that we just looked at. Might be in this one. No, it's definitely not in that one. Where are you hiding from me? Nope, that's about this. Here they are. Here they are. So this question is using this formula right here. And it gives you everything but V and asks you to solve, solve for V. So what do? We say 1 milliamp is the JD. So you do 1 times 10 to the negative third is equal to, and then the 1 nanoamp is the J0 or J naught. And you have 1 times 10 to the negative ninth is equal to E. And then you're going to have 1 over 0.026 as your value over there. So that's going to be VA over 0.026 as what the E is raised to the power of. So then you do some math over there. Again, we're going to have ln of 1 million on the left side is equal to V over 0.026. Okay. This is literally the exact same number that we calculated earlier. So it's just going to be 0.36 volts, which is the correct answer. Because then you take ln of 1 million. ln of 1 million is like 13.86 or something. Let's check that. Yeah, it's 13.81, sorry. And then you multiply it by 0.026 and spits out 0.359, 0.356 volts as your applied voltage. So that is simply using this equation. So this question, solving for the applied voltage given currents, is just, your JD equation right here. And just solving for V. So it's actually probably pretty easy. If you wanted to, on your formula sheet, you could write out, since this is a pretty common use of that equation, you could write out a version of the equation which is pre-solved for V. So it would be what? It would be JD over J0 is equal JD. It would be ln of JD over J0 times 0.026 is equal to VA, essentially. Because in this system, you know, ln of 1 million versus ln of 1,000,001 barely changes a thing. It's so negligible, we don't need to pay attention to it. And because of that fact, you can just completely ignore that -1 portion if you're solving for the voltage here. And you can rewrite the equation as I just said, but you don't need to. Obviously, if we all know algebra here, you write out down that equation, you'll be able to use it properly when it comes time to do so in the test. All right. Which of the following conditions increases the electron hole recombination of a PN junction diode? So this one for me was a little bit of intuition. I didn't know the exact reasoning behind it, but for some reason, the reasoning that I just came up with in my head, which I probably didn't invent, I probably heard it somewhere, was the reasoning behind why I got it correct. So let's think about this. Recombination in a PN junction diode. Traditionally, we remember recombination from MCDEs, like recombination rates and all that stuff. So recombination is dependent upon your lifetime, right? Your carrier lifetime. Obviously, your recombination rate won't change if your carrier lifetime is constant. So they need to think of another way to increase that combination rate, right? Well, let's think about this. Put it into reverse bias. All that does is increase the depletion width. Nothing's flowing. The only change is that the depletion width has grown and the magnitude of the electric field is increased. There's not going to be much recombination there. Let's look at equilibrium. Nothing changes in equilibrium. Your recombination rate's not going up. High carrier mobility. Mobility shouldn't change recombination at all. We're looking at lifetime for recombination. So mobility is out of the picture. That only leaves forward bias. Now you can do it that way by process of elimination, or you can do it this way, which is the way I was able to pick forward bias. When you think of recombination, like let's think of magnets in recombination. This is just an abstract way of understanding like the reasoning why forward bias is correct. When you take, let's say, a couple magnets and put them on a table and then flick one of them towards the other, they're going to connect to each other, right? Okay. Now, if you put a bunch of magnets on the table and flick them together, they're all going to chain reaction after they bump around and they're all going to connect with each other, right? In the same instance here, forward bias means there's a lot more carriers being produced and sent through because there's a flowing of current through the system. That flowing of current through the system is causing a lot more carriers to be generated because it's in the forward bias. Therefore, that overall, there's more recombination happening because more carriers are present in order to recombine in the first place. When it's under the forward bias, more carriers exist in order for you to allow to recombine. If there's more carriers, more recombination occurs. So that's the only thing. You need to look for the answer that generates the most carriers. Therefore, forward bias is the only answer that can work. All right, 22. Which of the following diode parameters decides the color of an LED? This is straight up from his this one. This is straight up from his applications thing. But luckily, I knew this one beforehand because I liked LEDs for a while. I was obsessed with them. So let's look at the answers that weren't correct. Minority carrier lifetime, that doesn't do anything here. The doping in the NMP region, that definitely doesn't have too much an effect here. The applied voltage across the diode, if that were true, the more voltage you would apply to a specific LED would cause the color to change. That's not the case. We can look at the last one, the band gap of the diode material. The band gap, if you guys, we're all electrical engineers, we've all taken physics 3. If you remember correctly, the band gap, the more or less energy an electron has to emit to jump down from a higher energy level to a lower level, which emits a photoelectron or a photon or whatever, that band gap is what causes those wavelengths to change, right? So the band gap of the diode material is what directly affects the color of its, emitted photons. So the band gap's the only answer here. And that's straight out of physics 3, if you guys remember that. All right, so that's just a quickie concept question. There's no calculation to be done there. All right, consider an NP junction with ND much greater than NA, meaning the doping density in the N side is much greater than the P side. Which of the following is true? I answered this wrong because I wasn't paying attention at this point. I can explain the answer though, the reasoning why all options are correct. So ND is much, much, much greater than NA in this PN junction. Therefore, if we were to look at the depletion region of this junction, this is why my answer is wrong. Most of the depletion layers on the P side. That's right, because all options are correct. But obviously, if all options are correct, there's a reason that everything's right here, right? The electric field peaks at the metallurgical junction point. That's always correct. If we go back to that cool figure, regardless of doping densities, that metallurgical junction point, however close it is to one side or the other in the depletion width, is always happening. That junction, that electric field point, that max electric field is always at the junction point. So if you know this, which is true, because if we remember, same thing here, higher the doping density, the smaller its portion of the depletion width is. So you know if ND's orders of magnitude higher than NP, this thing's going to look like a sliver on the ND side and a massive chunk on the NP side. That ratio is going to be way off. It's going to be like 0.1 versus 0.9 or something even bigger. Because of that, we can know this is correct. Most of the depletion layer is on the smaller side because it's much less, has a smaller doping density. So we know that's correct. We go on to the last question. This is a general fact. The electric field always peaks at the metallurgical junction point. We know that's true. So you don't even need to know that this third answer is true. As long as you can confirm that 2 of these things are correct, you know all options are correct. Because that's the only possible thing in this one selection.
Hey.
Right? Yes?
Hey, I don't know if you guys already went over this, but can you go to one of the resistivity ones? Because I'm not sure what formula to use.
Yeah, so we actually just talked about that. So I can explain that real quick without having to go back to them. So there's 2 formulas. When you say resistivity, are you talking about under bias or equilibrium?
I guess both.
Okay, so when it's at equilibrium, the resistivity is still, there's still the same thing. You still have to use it the same way. So we have 2 formulas that were, well, 3 formulas if we're including all versions that we need to look at. So the first off is the general resistivity formula, which is, you know, rho is equal to, is the P called rho? Is that the proper term?
Yeah,
I think,
rho,
okay,
yep.
good. All right, 1 over Q times the quantity mu N times ND plus mu P times NA. So that's the general formula. Now, obviously, the general formula doesn't work for a PN junction because the material's resistivity changes based off of where you are positionally in the junction. So you can't just have a blanket resistivity for the whole thing, which is why you need to use depending. So we'll start with it at equilibrium. So at equilibrium, boop, 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 boop. Where is it hiding? I know he's got it somewhere. Maybe it's over here. No, this is a review lecture, huh? Nope, it's probably maybe here. It's hiding somewhere. All right, so here's what we start with. So this is the equilibrium carrier density. This is that formula we're looking at. Your nx times your p of x is equal to ni squared at any given point across the any given point across the PN junction. So when you're asked to solve for resistivity, it's going to be in one of 2 places traditionally. They're going to ask for you to solve the resistivity, and this is for equilibrium, in a neutral region, whether that be P or N, which, by the way, it should be the same in either one.
Yeah.
Or it's going to ask at the junction point. Most of the time, it's probably going to ask for it at the junction point because that's the more interesting solution. So when it's equilibrium, you need 2 formulas. You need that rho formula I just said, and this formula right here, which you can just write as N times P is equal to Ni squared. What does this mean? Well, it means that at the junction point, which in equilibrium is traditionally, you know, right at the center of the thing, we're considering this normally when they're symmetrical, but it doesn't necessarily have to be symmetrical. But when you reach that junction point or whatever, he has a graph of it right here. Yeah, you see those lines? That red line that goes down, that blue line that goes up when you go across? So you see that they intersect at a given point?
Is that
eventually.
the metallurgical junction point?
So the metallurgical junction point is where that black line is. Sometimes when they are symmetrical, like PN junctions, they will be at that point.
Oh,
but
okay.
sometimes they won't be. So what you'll have to do is you will have to find the positioning. What is it? So you will have to find, when it tells you to find it in the depletion region traditionally, right?
I guess. Well, our questions are shuffled in the practice quiz, but
Yeah.
the one where NA equals ND 10 to the 17.
Yeah, that's under bias, right? That's what the 5 volts, 0.5 volts.
No,
Your mic just went out.
this one's not under bias yet.
Okay, so
Oh
that one's
no,
not
this
under
one's not under
bias.
bias.
All right, and it has an answer, right? What was the answer for that one? Do you see it?
3,125 kiloohms.
Okay, let's go find that because I don't think
But-
we've gotten to that one quite yet.
Oh, okay.
Because we had a different one where it was under bias. This one.
Oh, yep. Yeah. So yeah, I plugged it into the base resistivity formula and I got something like ohms, like 0.0 or 0.312 ohms or something.
Yeah.
So I don't understand what we did wrong here.
All right, so what it should be is, all right, so this is symmetrically doped. So we can assume, since it's symmetrically doped, that the point where those two, like the holes and the electrons intersect is at the junction point here.
Yeah.
That simplifies this. What that means is that at the junction point, first off, the amount of holes and the amount of, the quantity of holes and the quantity of electrons are equal to each other at that point. So what does that mean? That means your P and your X are equal to each other at that point. So you can just pick either one. So let's see, if it's N times P is equal to Ni squared, we know Ni squared is 10 to the 20th power. And we know that now if these are equal to each other, N times P is simply going to be, N or P squared, doesn't matter, they're the same. So we'll just say N squared. Solve for that. Square root of N, square root of 10 to the 20th is going to be 10 to the 10th, right? Now you have 10 to the 10th.
So do we not use the doping values here? The A and the D?
Not at this point.
Okay.
So if you were finding the resistivity in either side, you would have been right. Because what would have happened is it would have been on one side, your NA, it's 10 to the 17th, and then 10 to the 3rd, right? And then on the other side, it's 10 to the 17th and 10 to the 3rd, but it's inverted, different values. But when you get to the center, it gets a little wacky. So since we're asking at the metallurgical junction point, we have to use that relationship, N times P is equal to Ni squared, in order to solve for that same level of decreased carriers at that portion. So now, if you plug into the general resistivity formula instead, 10 to the 10th, see what you get. You should get the big number. You should get the big number that I didn't pick because I'm stupid. But you should get the right number this time. Because if you think about it, 100, which is your mu values for both, times 10 to the 10th is just going to up it by like 1 or 2 orders of magnitude. And then plus that is going to have 2 times it. And it's going to be like, 1 over like 10, 1 divided by like 10 to the 7th or something. It's going to be ridiculous. Like a big time, like a small number in the denominator.
Okay.
One big number, right?
Yeah, I guess where I messed up was I wasn't using Ni. I was using those doping values.
Yeah. You
but
have
those
to
are
use...
just there to trick you, I guess.
Yeah, well, same issue for me.
Yeah, so the trick is, so here's something you got to remember though. The trick is it's at the junction point, it's not always necessarily Ni. You have to solve for that independently each time. Like we just got lucky that this is a symmetrical one, because it will be Ni when it's symmetrical like this, because at that point, since that relationship holds and it's always going to be equal to Ni squared, if the values are equal to each other, therefore squared, then obviously it has to be equal to Ni, but it can change. So you just have to work that formula out each time. The relationship might be different, but it'll always give you a relationship to where you can solve for one of them. And since they'll be equal at any given point, or you can solve for one of them, then you can use that relationship to solve for the other. Like for example, if it said N, like ND is equal to 2Na, then your relationship would be 2Na squared is equal to that, and then you'd solve through and find your Na. And then you could solve for the other one using that same relationship. Let's scroll back to where we were. Where were we? This one, all of the options one. So I went over why this is the case. All of the options are correct because you can confirm this is true and you can confirm this is true. As long as you can confirm 2 of the 3 things in an all options question, you don't have to waste the energy on the third. And you can be good. With the same reasoning, most of the band bending is on the P side, follows suit because most of the depletion layer is on the P side. Most everything is occurring in the P side because it takes up the greatest magnitude of the depletion region. All right. Does anyone know this one? This is one question I have. I'm not completely solid on. Do we have any formulas for capacitance anywhere? I haven't been able to look around and find them yet.
No idea.
Let's see. Capacitance. Ba, 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 ba. That's a diode. Applications. I feel like it might be here. Varactor. Yeah, this says capacitance somewhere.
I see something on the quiz 3 lecture 16. If you just control F cap. Keep going. There's a couple lecture slides. Slide 27.
Oh boy.
And 26.
Yeah, I was just here on the previous one.
Okay.
But they're different, like the Varactor diode.
Maybe.
All right. Voltage controlled capacitor using oscillators and detectors. So this is an application question. So we have parallel plate and capacitance, which is cool. So, okay. Okay. So here's his version of the capacitance formula written in terms of the Varactor diode. So this is a formula you can write down, but now I understand the question. C is equal to obviously epsilon silicon, which is what 11.8 times 8.85 times 10 to the negative 14th is the numerical value of epsilon of silicon, which is materially dependent, over the depletion region. You see that relationship, and now everything's clear. Why? Well, which of the following is true regarding the capacitance of a PN junction diode? The correct answer here is the capacitance of a PN junction diode is higher under forward bias compared to reverse bias. Well, let's look at the visual reasoning. So here's a higher capacitance. Why is this a higher capacitance? We can just look at this. This is all we need to see here. The traditional parallel plate capacitor formula. The smaller the distance between your parallel plates, the higher the capacitance. So that's just how a traditional capacitor, when it comes to parallel plate capacitors, works. That's its formula. Well, that principle, as it says here, is essentially mirrored. Our plates are now the edges of our depletion region. Thereby, the smaller the depletion region, the higher the capacitance of our diode. Therefore, the forward bias is the proper method to increase the depletion region, or increase the capacitance by decreasing the depletion region. Reverse biasing it is going to cause the capacitance to drop because the plates, per se, the edges of the depletion region will move farther away. Forward bias to move closer together. That's how you answer that question. And that's the formula we'll write down later. We're getting there. So that's why that's that. Cool. That did not take long.
Hey, what else does forward and reverse bias affect besides the depletion width?
Basically nothing. No, everything else is dependent upon that depletion region. That depletion region carries through. The only thing that changes markedly without being directly related to the depletion region is the built-in voltage? This is the incorrect slide for that. This is the slide we want. So the change is the built-in voltage is still the same. As you can see, here's how the so this is what it looks like. These are the equations when it's in equilibrium. And this is the equations when you have an applied voltage or a biasing, whether that be forward or reverse.
Okay.
So all it's going to change is the depletion width is the first thing that's affected by applying a bias. And you can see the only thing that changes is the depletion, the built-in voltage is going to change. And it's either going to go up or down depending on the sign of that applied voltage. Because if it's, a negative applied voltage times a negative, that total is going to sum and go up.
So negative applied voltage means reverse bias, correct?
Yes, because what's going to end up happening, if you think about it across the board, everything else remains constant here. We know the only changing thing is that we're subtracting an applied voltage. If the applied voltage is given to us as a negative sign, let's say our built-in voltage was 1, which it probably would never be, and our applied voltage was 0.5, negative 0.5. Well, if it's negative 0.5, it's 1 minus 0.5. That's 1 plus 0.5. Therefore, it's 1.5. 1.5 is bigger than 1. So the overall depletion width will increase because it's not in the denominator. It's a it's a numerator operator because it's being multiplied across numerators as opposed to being summed down a denominator and simply being square rooted. So overall, the overall depletion width will increase in reverse bias, as we know, because that's why. That's the numerical reasoning behind why when it comes to calculation. So the actual built-in voltage will not be affected, but right here, because as you see, like if we go here, built-in voltage has its own formula and it's not rewritten. It stays the same. What does change, if it ever asks you to calculate the junction voltage, it's the built-in voltage minus this, which you can also do. You can also calculate the junction voltage using depletion region ratios times the built-in voltage, which we did in equilibrium. But since you don't have to do that, when it's under bias, you don't need to do that. You can simply just do this. This is easier, so do it that way. So what did we do? We did this. Let's look at this. Which of the following is true about the energy barrier that keeps electrons on the N side and holes on the P side of a PN junction? This is straight out of multiple choice, or straight out of true and false again. Just adds more possibilities. Well, that energy barrier it's referring to is our electromagnetic field that's in the depletion region. So what happens to the depletion region when it's under forward bias? It gets smaller. Well, the electric field is less area to operate in. It's going to decrease. That potential energy barrier that keeps electrons and holes separate is going to drop. It's going to go down. It's going to lower or decrease under forward bias and increase under reverse bias. That's that. It's the same question from earlier, like a lot earlier. They just gave 2 more possibilities, as opposed to saying true false. They just worded it 3 more times. If N side doping density of a PN junction is twice the doping density of the P side, which of the following is true? So I answered this wrong because I'm a nerd. Let's look at this. So the correct answer is the maximum resistivity point is on the P side. Maximum resistivity point is on the P side. So first off, the real reason that my answer is extremely stupid is because I said the maximum electric field point is on the N side, when we know that regardless of the PN junction, the maximum electric field is always at the junction point. It is never anywhere else. It is always at the junction point. It's never going to be one side or the other. It's always at the junction point. The only thing that changes is how steep that slope is to the junction point based off the area that is taken up by each doped side. So that's an obvious wrong answer. I was probably hungry at this point. Depletion layer width in the N side is double that of the P side. That's wrong. So there's a reason you can tell that wrong answer is actually wrong. And it's because when the N side doping density is larger than the P side doping density, that means it takes up less depletion width for its side. Because the higher the density of a doping side is, the less width it takes up, because volumetrically, or volume, like in a given volume, the more dense you are, the more of your stuff is in a certain volume. So it means that you have a higher concentration of charge or carriers in a smaller amount of volume, higher density. Therefore, the depletion layer width is not double on the N side. It's smaller. And
it'd be half.
Yeah, I don't know.
Smaller.
It should be 1/3 on the N side and 2/3 on the P side, if you work the math out. But yeah, something like that. It should be small on the N side, even though it has a higher density, and it's directly because of that higher density. The last one you can say, so another one, a maximum electric field point is on the P side. We know the maximum electric field is always at the junction point. It's never on either side. And then the last thing, the correct answer, the maximum resistivity point is on the P side. So let's look at this So in this one, this is actually the direct inverse of that question. Obviously here, the P has the higher doping density, but either way, we can use this as an example. So look, you see where those carriers are equal, where they cross each other, and it's not at the junction point? That, where those carriers are equal to each other, is the highest resistivity. So this figure is the exact inverse of the question. So if we were to invert it, then you would obviously see that where those carrier densities are equal to when they cross each other on the N side here, you flip it and that's the P side, you can see that the maximum resistivity point is in fact on the P side. So that's just a graphical way to represent that. But mathematically, you would just calculate when, at this point, when you're equal to N squared or P squared, whichever you like, your maximum resistivity point is there. And it's going to be on the side with the less dopant, or the smaller doping density. It's going to lurch to that side. That's just a general rule. But like figure-wise, if you draw out your figure, these lines will always end up on the side. When it's symmetric, this will end up on the junction point, and when it's non-symmetric, the maximum point of resistivity will be on the side with the smaller doping density. That's a rule that should hold across all instances, biased or equilibrium. All right, question 27. We're almost at the end of this. Which of the following correctly describes the effects of temperature on a p-n junction diode? I said all options are correct, and all options are correct. Let's explain why they are all correct. Higher the temperature, lower the built-in voltage. We know that because more carriers are released in the system, and that causes the Fermi levels to get a little bit closer together, causing the built-in voltage to be smaller. That's from all the way from the beginning. This question was asked earlier, or that specific question was asked earlier. So we know that that's true. Higher the temperature, lower the built-in electric field. That is also true. If your built-in voltage is lower, your electric field is also going to be lower because everything's affected across the board. If your built-in voltage is smaller, your electric field's also going to be smaller, and everything's just going to be much less in magnitude. All the magnitudes are going to drop across the board. And then higher the temperature, larger is the diode saturation current. That is also true. Where's my diode saturation current formula? It's the really big one. We're getting close. We're getting close. It's right here. Here's your diode saturation current density. Well, we need to find why temperature makes this bigger. So we need to find how temperature can possibly factor into this relation. Well, we have a relation. It's called the Einstein relation. And it allows us to look at this formula, and you see that dP and dN. And we can look at that formula and find out that dN is going to end up being equal to mu times kBT over Q. Well, there's a T in the numerator for both parameters, dP and dN. Therefore, every time that T goes up, the general overall value of your saturation current will follow and go up. So that's just a case of being able to look at this monstrosity of a formula, go understand that you're going to have to, go look at the Einstein relation from all the way back in our first quiz, and then be like, oh, temperature's in the numerator, it's going to go up. So that's all that one is there. A lot of these things are just straight up just looking back at formulas and understanding what affects what and how. It's basically just concepts and concepts and concepts. That was this one. The space charge in the depletion region of a p-n junction is due to, the correct answer, negative ions in the p side and positive ions in the n side. So space charge in the depletion region is described here. So we call this the space charge region. So right here you can see space charge is illustrated by negative ions in the p region and positive ions in the n region. That's exactly the correct. Negative ions in the p region, positive ions in the n side. All you need to do is memorize this figure and understand that in the depletion region or the space charge region, whichever you want to call it, the p-type, which traditionally when you think of p-type, you think of the majority carrier being holes, being positive, right? But in this case, it's not, because they actually reverse. Because of the electrostatics of that central area, they pull away and pull apart towards each other. And it causes it to be negative positive instead of positive negative. How you would expect, which is why I answered this wrong, because I didn't look back at the figure. So that's just that. That's just something you just need to remember about the space charge region. P is negative, N is positive within that portion. Question 29. What is the built-in voltage of a silicon PN junction whose N side doping density is 10 to the 16th and P side doping density is 5 times 10 to the 15th? Well, that's just a formula. Built-in voltage is 0.026 times ln of 10 to the 16th times 5 times 10 to the 15th over 10 to the 20th. You work that number out and it's just 0.7, which, by the way, you can immediately rule out two answers here. Anything over 1.12 is wrong because that's greater than the band gap of silicon. That's a no-no. That's never going to happen. So 1.2 and 1.7 are already out. So from there, if you were guessing, you could just do that, but you don't even have to. You can just work this out with the formula. It takes less than 30 seconds.
Right, and I think the formula for that would VBI is equal to, I think it's like NA/ND over something.
Yeah, so VBI is equal to, officially, I'll tell you everything without plugging any numbers in my head. It's KT over Q times ln of NA times ND over NI squared. Intrinsically, there's a bunch of stuff here that can be automatically plugged in because there's a lot of constants. So the way that I remember it is 0.026 times ln of NA times ND over 10 to the 20th. And that's going to yield you your built-in voltage. Because Ni is a constant, so Ni squared is a constant, and KT over Q is a constant.
So are you also do you already have a formula sheet for this quiz? Have you built one yet, or are you just?
No, I have a formula sheet from the last quiz or the midterm, but after all, PN junction was on that. Obviously, it was on the equilibrium PN junctions, but because of that, roughly half of our formulas are going to be equilibrium PN junctions, so I already have them pre-written. This time, since this is run a little long, what I'm going to do is I'll make my own formula sheet tomorrow morning, and I'll send it out to GroupMe so everyone can look at it and just take it if they want. Because I have 2 exams tomorrow, and I have an 8 a.m. one, so I have to get to that one at some point. I have my calc exam.
That'd be great. Thanks.
Yeah, I will. I'll make sure to get that done. All right, this is the last question. Oh, we already did this. I forgot. We already did this. I'll go over it one more time since we did talk about it. So consider a symmetrically doped consider a symmetrically doped PN junction diode where Na and Nd are equal to 10 to the 17th. What is the resistivity exactly at the metallurgical junction point if mobility of both electron and holes is equal to 100 centimeters squared? We know the general resistivity formula, and we know that since this is at equilibrium and it's specifically at the junction point, we can just simply use the formula N times P is equal to Ni squared to solve for our carriers at the junction point for both Na and Nd, or N of X, P of X is what you should call it, because Na and Nd are values that you have at your neutral regions. And the reason we say N of X times P of X is because our N and P values are varying dependent upon our X position within the junction. So it should be called, let's call it like it is, but either way. Doing that, we know at the junction point, these are equal to each other at the junction point. So we can simply say, instead of saying N times P is equal to Ni squared, we can say either N squared is equal to Ni squared, or we can say P squared is equal to Ni squared. Doesn't matter. Pick one, doesn't really matter. Then what you do is you will do N squared is equal to 10 to the 20th, square root that. N squared is equal to 10 to the 10th. There you go. That's the value, and that's the value for both of them since we know they're going to be equal at that point. So then our resistivity is going to end up being 1 over Q, which is 1.602 times 10 to the negative 19th, times 100 times 10 to the 10th plus 100 times 10 to the 10th, parenthesis. You work all that out, and you'll get 3,125 kilo ohms per centimeter. So that's all it goes for those ones. Yes?
Yeah, why don't you plug in Na for, I guess, P here?
Okay. So the reasoning behind why we don't plug that in there is when you're given Na and Nd in relation to a PN junction, Na is this, like this would be your 10 to the 17th, and Nd is this would be your 10 to the 17th. This obviously isn't symmetrical, but when you're given those values, it's telling you the majority carrier density in both of the neutral sides in this case. It's giving it to you in your P side in form of Na, and it's giving it to you in your the N side in the form of Nd. So when we're asked to solve at the junction point, the carrier densities, as you can see by those lines illustrated, that they change across the board. They need to go meet at one point and invert to get to the other side in order for this to be proper. So that's why we can't simply plug in 10 to the 17th, because remember, another trick is because at this point, because this is not like this isn't like MCDE where we can just say, you know, oh, there are this many excess carriers. You can't say like it can't be over 10 to the 20th. At any given position in the PN junction, the maximum amount of carriers is equal to 10 to the 20th at any given point, because there aren't excess carriers in this system because it's under equilibrium. And because of that, that means you have to find it at the junction point, which is where it's equal. So it's where the values are going to end up crossing when it's symmetrical. This one is not symmetrical, by the way. This one is not symmetrical. It's slightly weighted to the right, but it's weighted by a linear relationship. So you'd solve it a slightly different way. Instead of saying, you know, n squared, you would say like 2n squared or something like that, because it would be related by a linear coefficient or linear multiple, like 2, 3, 4, something like that.
Okay.
So you can't use 10 to the 17th there, simply because 10 to the 17th times 10 to the 17th, you know, is what? It's like 34.
Yeah.
That's no good. That's too big. Wait. Yeah, it's 34. That's too big. 10 to the 34th is too big a number. It's way too big. That's basically it. It just need to make sure that like at any given point across a PN junction, that your carriers do not exceed 10 to the 20th when multiplied together. Like this would be 10 to the 17th, this would be 10 to the 3rd, this would be 10 to the 17th, this would be 10 to the 3rd. Therefore, at the center point is 10 to the 10th for both. And that's just how we solve for the resistivity in these questions. So that's that. That took longer than expected. Actually, not really. This is just about the 2-hour point, which is good. That's about how long I want these to max out at. I make these for a lot of classes, so I don't want these things to be too long.
I can look at the video, but do you think you could quickly explain the other resistivity problem? The one
Yeah,
where,
I can scroll back to it. I need to find it. This one. So he's all so far. So I think he's only really asked for symmetrically doped ones. When it's not symmetrically doped, he'll give you a relationship between the Na and Nd. Like essentially, because otherwise it's a lot more difficult to solve for at some given function like Px Nx. So here, the resistivity formula is the same, but we have a different formula to solve for Nx times Mp. That formula is going to be Nx times Px is equal to, and he said it earlier, but I gotta relook it up. I'm a genius. Where is it?
And I squared e to the qv
Sounds
over
about
kt.
right. Yes. Equals e to the qva. By the way, it's va.
Okay.
Va over, you said kt?
Yep.
All right. So first simplification of this formula. You can say it's actually equal to e to the va over 0.026. Let's set that equal to 1 electron volt over the numerical value of kt. So there's the first thing. And then you have nx times px, right? So, okay, so now let's go back to the question. So now we need to solve for new values nx and p. So you numerically evaluate the right side of that equation, which is going to be 0.5 divided by 0.026 to the e power. It's going to be some fat number. Let's see. A little damp on light. So 0.5 divided by 0.026. Yeah, big number. Big number.
Times 10 to the 20, that's 2.25 times 10 to the 28th.
Yeah, big number. So we have our big number. Now what we do is we look at what it's saying. It tells us that this is symmetrical once again. So that means we get to use the same process. You can either say n squared or p squared, doesn't matter. You take the square root of the number you just solved for, and that will give you your carrier density at the junction point for both, because they're equal to each other, remember? So you take the square root of your number, and then that number you get is what you're plugging into both Na and Nd in the general resistivity formula.
Okay.
And now when you do that, and you run across and you multiply by 1,000 instead of 100 here because it's got a different number, and you divide and everything, it should be equal to 20 ohms.
Okay. I got 20.8, but yeah, close enough.
Yep,
Okay.
there you go. All right,
That
so
was
that's how you
the
work.
trick.
That's how you work. Yeah. So for both forms of solving for resistivity, it's the exact same general resistivity formula. It's simply an issue of finding the formula for your carrier densities, which will change depending on whether or not we're under bias. Because obviously, as I said earlier, under bias we have more carriers in the system because you're applying an excess energy. So it's going to free up more carriers. And that's how it be.
So if it wasn't symmetrically doped, if it was like n is 2 times px, you
Yeah.
would just do it would
Yeah,
be like
so let's I'll explain like a quick version of that. I'll make the question myself. We won't full solve it, obviously. I'll just say we'll
Yeah.
say ND is equal to 3NA this time. Okay? So what does that mean? That means your NX and your NP are now going to be 3NA 3NA times your P, which is going to be, NA again. NA. So you don't actually have a numerical value. You simply have 3NA squared. So you have a variable still. So then that would be equal to your right side number. Instead of just square rooting it, instead you divide it by 3, then square root it this time, and that would be your new number.
and that would give you
That would give you the resistivity at, because remember, resistivity is where they're the same. Resistivity is not at the junction point.
oh, okay.
No. Let me say that again. Maximum resistivity is where they are the same. What we just solved for is resistivity at the junction point because of that changing ratio.
So they're not the same. So would we have to find n and p here? It would probably have to give you one, I think. I'm not sure how to do that.
Yeah, let me think about that. Because what I just solved for, I'm pretty sure is still just the max resistivity. Wait. Yeah. I don't remember if we've ever done one like that. Let me check my homework. Find the value of resistivity at x equals 0, which is the junction point. At x is greater than, like, just all the way on the n side and all the way on the p side. Yeah, we never solved for resistivity. Wait, let me see if that was a non-symmetric one though. This was C. Yeah, find the electron hole densities at x equals 0. Yeah, no, this was symmetric, wasn't it? Yeah, this is a symmetric one. Yeah, I'm not exactly sure. Let me look at this for a second. Let me look at this. So how would I solve for the resistivity at the junction point? The maximum resistivity point is there. No, I'm not sure. We might have to, that might be worth an email or a look through lecture. The reason we might not know this is because we might not have to do this, but I'm not sure. I don't know if we've seen an example of it or not yet.
So if it asks you to find resistivity, it's probably either going to be
Yeah, it's probably going to be
When
at
they-
the junction point, or it's going
when
to
they
give you the
cross,
values. Yeah.
or yeah. Okay.
Yeah, so it's either going to be when they cross. It's either going to ask find the maximum resistivity for an asymmetrical junction, or it's going to ask find at the junction point for a symmetric junction. Is all I can think
Right.
of.
Okay. Cool.
All right,
Seems good.
Baba Yaga. All right, now it's time for calculus. Yeet. I'm gonna stop recording. How do I do that?
I'm gonna make a Quizlet on these multiple choice questions.
Quizlet gang.
Yeah.
There's the stop recording.